Okay, so the next part is still informal. I want to go to this definition of a place, which is another way of saying a point, but not saying a point. Not my notation, okay, not my name. So I do want to give an informal discussion about this, and so that we can start it here and we can do it on the slides because it's mostly informal. So the point of this unit, which we are going to start now, but continue next week, or maybe an hour altogether, is trying to think of a point in a different way, actually 4 different ways. Okay. Okay. So, right. So these are the 4 different ways. So we are going to, first of all, connect points to maximal ideals, then to other stuff like valuation rings, evaluation places, and so forth. So, right. So I said informal, and now it looks a bit formal. So, but let's see. So there is a bridge between algebra and geometry that you might have heard of. How many knows about these things? Like, okay, you're good. I like the half, like the. By the way, my philosophy is that there is no bridge between algebra and geometry. There is no algebra and geometry. It's just the same thing. And we as humans kind of, understood this and understood that. And oh, it's the same thing. It's just us. It reflects on humanity, not on math. Okay, but we are humans, so let's go with it. So there is a bridge between algebra and geometry. That's why there is an algebraic geometry course, field, and so forth. And the idea there in general is that, well, at least initially what happens, I think initially what happens is that people prove things in geometry that were incorrect because they use kind of intuition and stuff. This was mostly, I think, in the French schools at some point in time. Italian, actually? Oh, sorry, just, yeah, sorry, French people. So what the French actually fixed it to some extent. German and French. In Italian school. At some point, not today, right? Good. So, yeah. And then, at some point it accumulates to like too much. So people started to rigorously try and prove geometric facts using algebra because you can't cheat in algebra. It's like you compile algebra. It's not intuition. That's the pros and cons in algebra. It's a code, and that's what you mean. But, so for example, what I'm going to show you now is that if you take a field, and now when you think of a field, you don't think of geometry, right? You think of like a field. It has addition, multiplication. So I'm going to take the elements in the field, the set itself, okay? And ignore completely the additive and multiplicative structure. So maybe if it's a finite field, then a prime field, then you have just 0 up to p minus 1, whatever. And because I want to kind of emphasize the fact that I'm not considering the field structure, we are going to write it like that. We are not going to write it. We're going to ignore it after this slide. But in general, people write like that. So it's A1, it's one-dimensional over F. A is for affine, so it's called the affine space over the field F, but don't worry about it. It's just a name, just writing F, while reminding ourselves that we don't care about the structure as a field. We only care about it as a set, and I'm lying. We care about it as a topological space, but I don't want to say topology. So I didn't say it, okay? So we think of it as a set. That's just a set. So it's geometric in the sense that you have points. Yes. Yes. Well, in 1 dimension. In 2 dimension, I will talk about the open sets will be the 0 set. Right, it's the recessive topology. So here, though, in 1 dimensions, it's still just finite sets, for example. Only in 1 dimension, right? And in a finite field. But let's ignore that. You see, that's what I don't want to say. But do ask me, and then I'll say just ignore it. These are good questions. But anyhow, this is a geometric object in this sense. After I kind of took away its algebraic, well, obviously it's nothing. So maybe we should call it geometric object. And I claim that this geometric object, there is an algebraic object that will kind of help you understand the geometric one. It encodes all the information that you care about, and you'll see in what sense. And that algebraic object is this thing. It's the polynomial ring over the field. Okay, so clearly, I mean, if I give you this, you know that. That's not what I mean. But let's just go with me and let's consider this ring, okay? All polynomial functions, all functions you can evaluate everywhere over the field. There are more functions that you, for infinite fields that you can consider, but I only care about these functions, these polynomial maps. Now, what I'm claiming, which is what's written here, is that there is it doesn't end here, it actually only starts here. So what's really happening is that every point in this field, and again, think of it as a point, so it's a geometric thing. So every point in the field, what I'm claiming corresponds to a maximal ideal of this ring. And every maximal ideal of this ring corresponds to a point in the field. So what I'm claiming is that there is a one-to-one correspondence between points and maximal ideals. Maximal ideals are the points. Okay. Now, how many of you don't, I mean, because the Galois is a prerequisite for this course, and I said several times that only from the mid of the semester, but I still need rings and ideals. So Tomer is going to give you a quick overview and introduction to these things, but in the next hour, but anyone don't know what is a maximal ideal? Can I ask this? Okay, so you are going to need to know, and Tomer will tell you, but you'll probably need like 3 hours. Okay, it's worth it. So what I'm going to say now is going to maybe be a bit like meaningless for you, but just catch up. So maybe let's just prove that for a second. Let's just prove as a. Or Tomer, do you prove these things? Okay. So maybe I'll just say it in a quick way. So why is it true that every point here corresponds to a maximal idea? Just to remind you, and this is actually not very far from the nature of the course. We're going to do, in a sense, somewhat less algebra than what's written here. It's not going to be that dense in a sense, but still. So I'm claiming that maximal ideals of this ring are in correspondence to points. So you have two directions. So on the one hand, if you take a maximal ideal, so if you take an ideal of the form x minus p, like they're generated by x minus p, well, I claim it is maximal. Why is it maximal? Well, one way to prove that an ideal is maximal is to show that when you quotient the ring by that ideal, you get a field. Right? That's an if and only if. When you quotient by a primary ideal, you get a domain, and when you quotient by a maximal ideal, you get a field. That's the two things that you need to know. And indeed, the quotient f of x over x minus p is isomorphic to the field f. It's not just some field, it's the field f. And the way you can show it, maybe I can ask you. How can you, usually when you want to show that a quotient is isomorphic to something, what do you do? Sorry? Right, but that's true, but that's why that's the image. But why? Exactly, good. So the first homomorphism theorem tells you that the ring, if you have some homomorphism, and you need to figure out what's the homomorphism, but if you have a ring and you quotient by the kernel of the homomorphism that you have in mind, then you get something which is isomorphic to the image. And as you said, if you consider, I mean, you kind of implicitly already said that if you consider the homomorphism that just evaluates the polynomial at p, takes a polynomial, evaluates it at p, it's a homomorphism, then its kernel is exactly x minus p. And it's isomorphic to f, that's what you said, and that's why that isomorphism is true. By the first homomorphism theorem, isomorphism theorem. That's what's written here in this thing. So this means that this is indeed a maximal ideal, which shows that any point corresponds to a maximal ideal. Now in the other direction, I claim that every maximal ideal of this ring is of this form x minus p, and I think that I forgot to say that I'm assuming that f is algebraically closed, because otherwise it's not true. Right, so in this unit, we are going to assume that f is algebraically closed. Our fields will never be algebraically closed because they are finite. But just for now, let's assume it's algebraically closed. We're not going to use it. It's just an informal introduction which looks formal, but it's an informal introduction. Okay, so on the other hand, because F is a field, we know from commutative algebra, like basic commutative algebra, that the ring of polynomial is one variables over this F is a PID, principal ideal domain, namely every ideal is generated by a single element. Like the best thing you can hope for from a ring, essentially, more or less. And because, so this means that every ideal, I want to show that every maximal ideal looks like this, x minus p. So this is one step. It at least tells you that every ideal is generated by one element, meaning one polynomial, but not necessarily maybe of the form x minus p. But then, because F is algebraically closed, the only way for this ideal generated by some polynomial F to be maximal is that if it's degree 1. Because if it's not of degree 1, you can find a factor x minus p, and the idea generated by that will be larger. Good, so this means that the degree of F is 1, and which means that you can easily write it as x minus p. So, it was quick, and I don't know, if you know these things, you just saw it, and if you didn't see it or don't know, clear if you don't know what maximal ideals are, then it's blah, blah, but, hopefully that's clear. Questions? It also works in 2 variables, luckily, but it's harder, much harder, essentially. And Tomer will show that because it's harder. I don't want to show that. It turns out that there is again, a bijection between the points in the plane and the maximal ideal of the ring that you would think, like the ring of polynomials in 2 variables, like the Reed-Muller compared to Reed-Solomon. And the maximal ideas look like that. You see, so you see the point here, like the 2 generators are from x minus something, y minus something, and that's the correspondence. That holds for any number of any dimension, and that's essentially the content of the weak Hilbert-Mulch-Stern-Satz. Okay, so Tomer won't prove to you the Hilbert-Mulch-Stern-Satz. It's a famous theorem in algebraic geometry, the basic algebraic geometry. He will just prove it for 2 dimensions, and even that will enable you kind of to remember things you might have forgot about UFDs and ideals and prime ideals and irreducible and prime elements and all of those things, you'll see it there. So don't worry if you need a brush up. And it turns out, maybe I should end with that, it turns out that it also holds when you do the right way at the Reed-Solomon, Reed-Muller, and then what I said would be algebraic geometric codes. Namely, you have a curve and you evaluate them. So it turns out that this also holds there, like this correspondence. Namely, say you have this f, which I called g before. F is a polynomial in 2 variables, and I'm using that to define the 0 set, over which I'm going to evaluate at some point when I'm going to do coding theory. But at this point, just consider the set of zeros of f, z sub f, like the subset of the plane. And what Hilbert-Mulch-Stern-Satz and what we did before in a simple thing from commutative algebra will tell us that now the ring that corresponds to this set, now this is kind of a geometric object in a sense, right? You can do that. But really the geometry is topology that I'm not talking about, but the geometry of this set, so this is the geometric side and this is the algebraic side. So what do we have here? We don't have the ring of polynomials in 2 variables because we need to encode information about f. What we have is this ring, this quotient. Right, so this is the ring of bivariate polynomials, but we think of 2 polynomials as equal if their difference is divisible by f. Right? If their cosets are the same. Like g and h are the same here if g minus s is divisible by f. If f is nice, like irreducible or absolutely irreducible, but then this is a domain, and we will talk about these rings are nice if the polynomial is nice and so forth. But what's important is that, again, a point on the curve corresponds to a maximal ideal in this ring. So this turns out to be a maximal ideal in this ring. And when you write this as ideals, right, it's the idea generated with respect to this ring. Yes. Okay, so we'll meet up next time and continue this informal discussion about points.